Welcome to the special plenary session, The Top 10 Greatest Challenges Facing the World Ocean. I'm your host, Dr. Chris Verlinden, oceanographer and co-chair of this year's GEO 2050 event. Today we will be discussing 10 topics of concern for the world ocean, 10 ways in which the ocean is changing, and not for the better. But there is hope, and we will also be talking about what you can do about every single one of these topics. The 10 topics of concern today are ocean acidification, global ocean warming, sea level rise, sea ice loss, coral reef loss, ocean deoxygenation, mangrove deforestation, ocean plastics, ocean noise, and overfishing. 9 of the world's leading experts in their respective disciplines and I will be discussing each of these 10 challenging issues. My colleagues here today represent leading international experts and exciting rising stars in the community. I will be starting off today's session by discussing a topic that is near and dear to my heart. I wrote a paper a few years ago discussing a proposed method of remote sensing of ocean pH using acoustics, and the next topic was my primary motivation. Ocean acidification is one of the most fundamental and straightforward topics we will be discussing today. Now, in order to understand ocean acidification, we need to first talk about what is meant by the term acidification. Not surprisingly, the term acidification refers to when a fluid, in this case the ocean, becomes more acidic. But what is meant by the term acidic? Well, acidity is typically measured on the pH scale, which ranges from 0 at the most acidic to 7, which is neutral, and 14 at the most basic end of the scale. To put it in terms of household chemicals, which you might understand and be familiar with, vinegar, a common household chemical, has a pH of 2.5. And since that 2.5 is lower than 7, lower than neutral, that means it is very acidic. Sulfuric acid, which you might have heard about in high school chemistry classes or even used, has a pH of 2.75. On the other end of the spectrum, we have baking soda, or sodium bicarbonate, which has a pH of about 8.3. And again, since that 8.3 is higher than 7 or greater than neutral, that is a basic chemical. Milk of magnesia, or magnesium hydroxide, has a pH of a whopping 10.5, making it extremely basic. Now that we understand the term acidification and what is meant by acidity, we need to talk a little bit about how and why the ocean is becoming more acidic. Well, it's fairly straightforward. The cars we drive in, the planes we fly in, and the power plants that produce our electricity all produce carbon dioxide as a byproduct of the combustion reaction which fuels these cycles. And that carbon dioxide then spreads around the world ocean and comes in contact with seawater everywhere. And when carbon dioxide comes in contact with seawater, it disassociates into carbonic acid and bicarbonate and free hydrogen ions. Now, the definition of pH that we didn't discuss earlier, the strictly mathematical definition, is the inverse logarithm of the concentration of free hydrogen ions in the fluid. So what that means is if we increase the level of free hydrogen ions, we make the fluid more acidic, dropping the pH. So as we produce carbon dioxide, that carbon dioxide interacts with the ocean, disassociates into carbonic acid, which as the name suggests is acidic, which raises the concentration of free hydrogen ions, thereby decreasing the pH of the ocean, making it more acidic, and overall a less comfortable home for marine organisms that rely on a fairly basic or neutral ocean for their well-being. You don't need to take my word for any of this. Today we're going to do a very brief demonstration in the laboratory of ocean acidification, starting with a combustion engine, exposing seawater to that combustion engine, and watching what happens, watching the pH drop. Thank you very much. So we're going to start off with a sample of seawater right here. I am going to pour the seawater into 2 equal sample vessels. So you can see that both of these samples of water come from the same source and have the same initial pH. I'm going to measure the pH using this pH sensor, where this probe is inserted into the water, and on this screen, which we'll zoom into, you can see the pH of the fluid. So I'm going to insert the probe into the water right here and measure the pH. And if you zoom in, you should be able to see that the pH is a little over 7. Now it's dropping a bit, and I bet it will actually equilibrate out to, just under 7. But the water that comes out of your tap is fairly neutral. Now what we're going to do is we're going to inject water into one of these, CO2, into one of these 2 sample vessels, and we're going to measure the pH as we do that. Now if you want to do this at home, let's say over Thanksgiving with your family, You could use something a little bit less expensive, and these pH test strips used for pools or hot tubs will work just as well for your purposes. Now, in order to get CO2, you can blow bubbles into the water with a hose. But that's not very much fun. It doesn't really illustrate the internal combustion part of this whole problem. So I'm going to use this highly scientific leaf blower here. Now, remember, you might not want to try this part of it at home because I am a professional physicist, but still counts. So I'm going to start up my CO2 generator here, my highly scientific device. So you can see if you zoom in that just by running it for a few seconds, we were able to drop the pH to about a 6.5. We probably could have gotten it a little bit lower if we ran it for longer. Just to show you that it's not a trick, we will dip the pH sensor in that original sample of water, which remember came from the same sample vessel, and you'll see the pH on the sensor rapidly increase to closer to 7, back to neutral. So you can see that by running a combustion engine, which produces carbon dioxide just like your car, just like the planes we fly in, just like a power plant, and exposing seawater to that CO2, we were able to drop the pH, and in this case to a level that would be difficult to survive for many marine organisms. Thank you very much for that demonstration. You can see that that was done in my basement. The demonstration that we just saw showed the acidification process from a combustion engine to producing carbon dioxide, lowering the pH of a fluid, causing it to become more acidic. So we now understand the chemistry behind ocean acidification. Now we need to get a handle on the scope and scale of the problem and the current state of ocean acidification in the world ocean. Well, as you can see from this chart, a plot of ocean pH and CO2. On the y-axis on the left side is concentration in parts per million of CO2 in the global world atmosphere. And on the right-hand side is the average sea surface pH across the world ocean. So you can see between 1960 and 2010, the concentration of CO2 in the atmosphere due to the anthropogenic production of CO2 has raised from 300 parts per million to nearly 400 parts per million. And over the last 20 years of that same time period, the average surface pH of the ocean has dropped from about an 8.1, which is fairly basic, to an 8.05, which is still basic, but less basic. And that represents a very significant change because remember, pH is a logarithmic measure. So 0.05 is significant. And what's more significant is if we carry those trends forward to 2100, you can see by the red line in this plot that it is anticipated that by 2100, the global average sea surface pH will decrease to 7.8 if we do nothing to change our current output of carbon dioxide. There is, however, a silver lining to this cloud because from what you can see on the blue line, if we curb our CO2 emissions significantly, then we can stop and even reverse this trend, increasing the sea surface pH back to natural levels. Now, in order to see this more visually, I want to show you this plot of global sea surface average pH in 1850. Now, this is estimated because we didn't have all the same measurement instruments, but I want you to see that the average ocean pH at the surface is well over 8. It's very basic. And this map is dominated by dark blue colors. And there's a little bit of light blue and certainly nothing going into the yellow on this particular color bar. Now, if we advance to today's ocean pH, we can see that the ocean is still largely basic, but less so. The average pH you can see is still just a little bit over 8, but only a little bit. and it's not a uniform distribution. The Pacific Ocean tends to be a little bit more acidic than the Atlantic Ocean, for example, and that's not necessarily of concern, because organisms that have evolved to live in these locations have evolved to live under these current acidity conditions, and that's okay. But now, if we look at the anomaly, which helps us understand what the trend in ocean pH is, it's a lot more concerning. The ocean pH anomaly, represented here in this plot, shows what would happen if we subtracted our current ocean pH from the average pH over the last 200 years, representing the pH difference between now and what has been the average over this period. And if we look at the anomaly, we can see that everywhere on this plot, the anomaly is negative, which means everywhere in the world ocean, the pH of the ocean is decreasing, meaning the ocean is becoming more acidic. And again, not uniformly. If we look at these red and orange numbers in the North Atlantic, the ocean pH in these areas has dropped by 0.12. On a logarithmic measure, this is an extremely concerning trend. And if we carry that trend forward, as you can see here in this plot, and show what the ocean sea surface average pH is expected to be in 2100, contrast this with the plot we saw a few slides ago of a dark blue basic ocean everywhere. We see this ocean is almost entirely light blue and even yellow, meaning the ocean is going from being extremely basic to almost neutral. And you might ask yourself, why does that matter? Neutral sounds okay. And on the surface, you're correct. But as is probably not surprising to you at this point, the chemistry of how biological reactions that marine organisms count on to survive has evolved over the millennia is for the current ocean conditions. And this is perhaps best represented by a measure called the aragonite saturation state, which you can see from this equation is basically the concentration of free calcium and carbonate ions divided by their equilibrium concentration. And what that essentially means is it represents a bioavailability of this type of calcium carbonate for chemical reactions such as organisms building their calcium carbonate shells or tests. They're building their homes. And so what you can see based on this plot of the aragonite saturation state in 1850 is that the vast majority of the ocean has a fairly positive aragonite saturation state on the order of 3. That means organisms can build calcium carbonate shells in the vast majority of the ocean. Now, if we continue the pH trend that we saw on the previous charts forward and look at the aragonite saturation state projected in 2100, we can see these massive regions of the world ocean which are orange and even red, which are areas where organisms would have a difficult time forming calcium carbonate shells and therefore would be unable to survive. So in short, what this plot is showing is that by 2100, significant portions of our ocean will be uninhabitable to a significant number of marine species. So who cares? You're not a marine species. Well, for starters, salmon care. And anyone and anything that eats salmon, from a grizzly bear to human beings. Now, the reason that salmon care about ocean acidification is that salmon are what's called an anadromous fish species, which means they spend some of their time in rivers and some of their time in the ocean. And when they're in the ocean, they love to eat these little critters called pteropods. Now, pteropods are a pelagic, meaning they live in the water column, free-floating, not on the bottom or not on the surface. They're a pelagic snail species, which, as you've probably guessed by now, form calcium carbonate shells. And, as you've probably also guessed by now, if the ocean continues to become acidic at its current rates, they will be unable to form those shells in the future. They are one of those species I mentioned that will not be able to survive if the ocean keeps becoming as acidic as it is. So this will have what's called a trophic cascade, which means if there are no pteropods, the salmon that eat the pteropods will be impacted. And then all the organisms that rely on the salmon, including grizzly bears and ultimately human beings, will also be impacted. So, in short, everyone cares. Everyone who in any way is associated with this food chain, which is all of us. So at this point, you might be asking yourself, what can I do? The fact is, all of these trends are extremely concerning. And you might be asking yourself, what can I do as an individual, as a private citizen, about this problem? Well, there's at least 4 things. The first thing you can do is support scientific research. What I mean by that is when there's a ballot on the election that says, should I increase funding or decrease funding for oceanographic research, particularly marine chemistry? The answer really needs to be increase at this point. The fact is we need to understand this problem better. We need better sensors that can measure the pH of the ocean in situ. We need remote sensing technologies that can measure pH all over the world ocean so we can understand the current state of the problem and make more accurate predictions about the future so that we can be prepared for what the future of the world ocean holds. Second, support initiatives to empower women in demographics that are underrepresented in the scientific community. Now, it's not always immediately clear what the links are between some of these socioeconomic and often politicized issues and a scientific topic like ocean acidification are. But it's been shown by statistics that a more prosperous community that has more educated individuals has more minds working on solving a problem like this, and that is always a good thing. In short, support initiatives to empower women globally and underrepresented minorities in the scientific community. Third, reduce your personal carbon footprint. Now, I am not an expert in this particular portion of climate science, but I interviewed a lot of experts in preparing for this talk, and some of these things are very simple. You can drive less and take public transportation more. Eat less or even no red meat. Eat a plant-rich diet. Get solar panels for your house. Reduce your food waste. Fly less, and maybe buy carbon offsets when you do fly. Minimize new product purchases, or insist through your purchasing power on sustainable supply chain management in the things that you do buy. And maybe reduce your house temperature a little bit in the winter and increase it in the summer to reduce the amount of electricity and power that you use, among a great many other things. Finally, communicate about climate change. Many of you in the audience might be professional educators, in which case, educate. If you are not a professional educator, educate. Talk to your friends, talk to your family. Maybe bring up the uncomfortable topic of ocean acidification over Thanksgiving dinner. Because the fact is, those of us who understand the problem, which now includes you, have an obligation to do something about it. And one of the most impactful things we can do is to start a conversation and open a dialogue between everyone who will listen, which for all of us includes our inner circles, our friends, and our families. So in conclusion, support scientific research, support initiatives to empower women and demographics underrepresented in the scientific community, reduce your personal carbon footprint, and communicate about climate change. Thank you very much. Like I said, ocean acidification is one of the most fundamental topics discussed here today because it is a direct consequence of the CO2 that we as people put into the atmosphere. Similarly, our next topic, presented by Dr. Greg Sennett, global ocean warming is a result of anthropogenic input of CO2 into the atmosphere. Dr. Greg Sennett is a postdoctoral researcher at the University of California, Irvine. An observational physical oceanographer, he studies processes affecting nearshore circulation, mixing, and stratification. As part of his research as an AAUS science diver, Dr. Sennett often uses equipment deployed in the dynamic nearshore environment to measure heat flux, internal wave dynamics, and other nearshore processes, with direct implications for coastal ecosystems. As an NSF fellow, Dr. Sennett has also developed high school earth science curricula focused on experimental learning techniques and making pioneering research accessible to and exciting for beginning scientists. Dr. Sennett earned a PhD from Scripps Institution of Oceanography in 2018 and holds MS and BS degrees from the University of Maine in oceanography and engineering physics. Thank you very much for being here today, Dr. Sennett.